Hi, my name is Nishant Garg with the C2000 System Applications team. I'm here to talk to you about two very useful C2000 features called real-time mode and real-time interrupts. In real-time control applications, debugging has always been a challenging task. Traditionally, a user would need to halt the processor to get information on whether or not the system was behaving as intended. However, in these applications, halting the program would mean stopping a power MOSFET's PWM output in an undesirable way. For a power supply, this could result in a blown-up power stage, or in motor applications, a stalled or damaged motor. For many processors, the solution is to provide a real-time debugger through a serial port mechanism. While this is workable, it is a rather cumbersome approach. With the C2000, the microcontroller, emulator, and Code Composer IDE work together to provide a simpler, more seamless approach. This solution, called real-time mode, allows for continuous feedback from the controller as it operates, without having to stop the processing. Real-time mode operation allows us to operate another useful feature called real-time interrupts. Like many controllers, the C2000 has the capability of running an interrupt service routine. This is a type of routine that executes whenever a certain external or internal trigger is received. When we are running a program while the controller is hooked up to an emulation software and hardware, a halt command will pause the running code at that instant, including an interrupt service routine it is addressing. So what happens if we need to debug our code, but have a critical process currently running? We would not want to do this because abruptly halting everything, as mentioned before, can damage our system. Real-time interrupts can help us with this issue by providing us a way to let the critical interrupt service routine continue to be serviced under a halt command while enabling us to debug other sections of our program. By configuring a few software bits appropriately, we can enable operation in real-time mode and set up a real-time interrupt to be enabled. Real-time interrupts can help us with this issue by providing us a way to let the critical interrupt service routine continue to be serviced under a halt command, while enabling us to debug our other sections of the program. By configuring a few software bits appropriately, we can enable real-time operation and set up real-time interrupts to be enabled. I'll show you an example of how to set up real-time mode and operate real-time interrupts. To do this, I will be using an experimenter board with a Piccolo F28035 control card, which can be purchased at this TI website. I'll also be using Code Composer Studio 4 along with the controlSUITE software package. Code Composer and controlSUITE are both easily downloadable from this TI website. Just make sure to go to the software page. Please also make sure to have the latest version of controlSUITE with the device support package installed for the F28035 control card. Let's start with this example project from controlSUITE. In the corner here is the display of my board and control card. Let's open Code Composer Studio and load the program for PWM real-time interrupts by going to Project, Import Existing Project, and navigating to the directory where the example is. By default, it will be under C:*TI, controlSUITE, Device Support. We'll be using an F28035 card. Go to the latest version. It'll be under Examples and scroll down until you get to real-time interrupts. Click OK and finish. Once that is loaded, if this is your first time using CCS, you will need to set up a new target configuration for your device by going to Target, New Target Configuration. Input a name for it, real-time interrupts. Select the connection. We'll be using a XDS 100. And the type of card here, again, it is the F28035 here, and click Save. Now we can start looking at the program. Expand the project directory in the CCS window and open the source file for this project here. This program configures PWM1 and enables an interrupt to be triggered at each period. It also allows for simple configuration of real-time mode and interrupts. I've written a few lines of code to initialize the LEDs on our control card, shown here. LED 1 is a green status light for power, and LEDs 2 and 3 are red. LED 2 will be rapidly toggled on and off from the main code routine, shown here, and LED 3 will be toggled from the interrupt service routine triggered by PWM 1, shown here. Build and load the program onto the controller by hitting the debug button. Code Composer will now take you to the debugger screen after it is done loading the controller. Here we can set up a watch window to facilitate our modifications and understanding of the program. This is where we will be able to debug code in real time and receive real-time updates. In a watch window like the one I have here, add these variables shown here and also listed at the beginning of the source code. You can open up a watch window by going to View, Watch. EPWM1 timer int count, the variable shown here, is a variable defined in the code to count the number of times the interrupt service routine for PWM1 is serviced. It increments by 1 each time the interrupt service routine is called. EPWM1 regs.tbctr, shown here, is a register containing the counter for PWM1. We will see that it will stop with an emulation halt unless the free soft bits are set. EPWM1 regs.tbctl.bit.freesoft, shown here, is 2 register bits for PWM1 to establish how the counter for the PWM reacts to an emulation halt command. The default 00 in these bits will stop the counter when a halt command is received. A 01 will allow the counter to reach a period end after halt command, and a 10 or 11 will allow the counter to run freely after a halt command is received. Remember though, that without real-time interrupts enabled, the interrupt will still not trigger even if free soft bits are set. On the C2000, interrupts are prioritized in hardware based on the type of interrupt that is to be serviced. This is handled by Peripheral Interrupt Expansion, or the PI module. dbgIER.int3, shown here, is a register bit that designates whether we want its corresponding interrupts to be designated as time critical. These INT bits represent the same groups of interrupts as the PI groups. Setting this INT3 bit will establish the PWM interrupts to be time critical and operate as real-time interrupts. Combined with setting the free soft bits, setting this bit will allow the interrupt to continue to operate after a halt command. Similar to the normal interrupt process again, there's a global real-time interrupt enable mask, dbgm, that must be cleared for real-time operation. This is done by the command ertm, just like EINT, shown here. Just to note, interrupts must still be enabled through the PI as well. Now we want to run the code. Hit reset, restart, and run. Notice LED 3 toggling on and off. This occurs each time the interrupt service routine is entered. LED 2 appears to be on constantly, but is really being toggled by the main code loop too rapidly to tell the difference right now. Also, note that the variables in the watch window are not displaying up-to-date values. This is because we are not operating in real-time mode. On Code Composer, now hit the Halt button, shown here. The watch window will now display the register memory contents. Notice the LEDs stopped toggling and remain in their last state. This is because we have entered what we call stop mode, and the main routine and interrupt service routines no longer run. You can see that if we step through the code as we show here, LED 2 will toggle on and off. However, LED 3 will not switch as PWM1 interrupt service routine is not serviced, because our interrupt has not been configured to be time critical. Note that this first approach is very similar to the traditional process for most microcontrollers. Now let's see the difference with real-time mode and real-time interrupts enabled. If we change our process to run in real-time mode, we can receive current values in the watch window or even on graphs. To enable real-time mode, click on the real-time mode enable button here. If CCS asks you to set the STI bit to 1, click yes. Click run again, and the LEDs will resume toggling. Now, look at the watch window and click the continuous refresh button here. The variables will refresh as the controller runs. We are seeing the status of the variables in the controller memory in real time without halting the device. Notice the timer int count and PWM counter turn red as they update and are incrementing rapidly. Set the free soft bit to 10 or 11. Here we'll put in a 2 or 3 to enable free run mode of the counter and hit halt again. Setting the free soft bits allow the timer to continue to increment even after a halt. The interrupt, however, is not being serviced because it has not been designated as a real-time interrupt yet. That's why the timer interrupt counter is not incrementing and LED 3 has stopped too. LED 2 has also stopped due to halting of main code. The last step to establish PWM1 timer interrupt as a real-time interrupt comes when we set dbgIER.int3. Since we are in real-time mode, we can just type in a 1 for the value and hit enter. The timer int count for PWM1 interrupt now continues to increment even though we are still in halt mode. Similarly, notice that LED 3 on the control card has resumed toggling and LED 2 remains stopped. This is because real-time mode is allowing the PWM interrupt that we designated to be time critical to be serviced during the halt command. To wrap the demo up, if we step through our code again while we're still in halted mode, we can see LED 2 toggle for each step like before. So this is where the strength of real-time mode and real-time interrupts lie. Limiting the number of times we need to halt our processor to receive feedback and debug our system can greatly increase our efficiency. We can significantly increase our understanding of our programs and even reduce possibilities of damaging our systems using these features. Now you understand how to run your programs in real-time mode and use real-time interrupts. I hope you will find these to be useful tools for you in the future. Thanks for watching.